Hello everyone, welcome back. Today we are going to talk about momentum conservation laws, and that means collisions. So to start out, let me show you a few collisions that I actually did myself. Here I'm going to start with two physics carts. They're both the exact same mass, they both have spring plungers on them, and I'm going to have them roll toward each other at the same velocity. So as you can see, they roll toward each other at the same velocity, they bounce off each other, and they both leave at the same velocity. So if we're going to think about this in terms of momentum, the cart on the left has a positive momentum, the cart on the right has a negative momentum. If the velocities are equal and opposites, that means those momentums are also equal and opposites, which means the total momentum would be zero. Since they bounce off each other in opposite directions at the same velocity, the total final momentum is also zero. All right, now I'm going to leave the blue car in place. I'm going to have the red car hit the blue car. Now, right before the collision, the red car is moving to the right, which means we have a total positive momentum. Hits the blue car. The red car bounces to the left slightly, which means it lost all of its positive momentum. Where did it go? It was given to the blue car. Now, if I do this a few times, something you'll notice is that pretty much if the first car that hits comes to a stop or a near stop, the other one leaves the collision at the same velocity the first one hit at. This phenomenon happens also if you play billiards. One ball hits another that was at rest, and the second ball moves away at the same velocity the first ball hit it. That's because there's a direct momentum transfer, and the billiard balls all have the same mass. Now I'm going to put a metal bar on the red car, which is going to increase its mass. I'm going to let it hit the blue car. Now if you notice, the red car slows down a little bit. It's still moving forward, but it slows down slightly. That means the red car is still losing some of its momentum, and it's giving it to the blue car. If I do this in reverse, the blue car hits the red car and actually ends up going backward a little bit, passing some of its negative momentum this time to the red car. Now let's change the situation. I'm going to set it up so these cars stick to each other. Watch what happens. The red car is moving at one velocity. When it hits the blue car and sticks, that velocity decreases. Even if I add more mass to the red car, you can see the velocity decreases after the hit. Let's try with the blue car. So the blue car hits, and you can definitely see the decrease in velocity. Now, the blue car had momentum moving to the left. When it hits the red car, their masses combine, and the velocity decreases. What happens to the momentum? Okay, so this next one, I'm going to take these two cars, and I'm going to run them into each other at approximately the same velocity. Now notice the red car still has a larger mass, which means before the collision, there's more momentum to the right. Now watch what happens. They hit, and now both these vehicles are moving to the right. Which means after the collision, there's still more momentum to the right. Now let's change the situation one more time. This time, I'm going to use the plunger. And I'm going to have the cars actually push off of each other. First, let's do it with the same mass. So initial velocity is 0. I hit the plunger, and they both move away from each other at approximately the same velocity. I will increase mass on both of them, but they're both still the same mass. Do it again. And they both move away from each other at the same velocity. So to stop here for a moment, that means initial momentum is 0 because the initial velocity of both carts is 0. Since both carts are the same mass and they move in opposite directions, one has a positive velocity and one has a negative velocity of the same value, so the final momentum is still 0. So let's do this one more time and actually change the mass of one of them. So the red car again has more mass than the blue car. I hit the plunger and they separate. Now, if you notice, the blue car left with the higher velocity. So initial momentum is 0 for either of them. But if I give one car more mass, they still move in opposite directions, but the one with the larger mass has a smaller velocity. But something to keep in mind, their momentums are still in opposite directions. So let's have a little deeper discussion about these three collision types. So let's do a little testing here, and along the way I'm going to show you the three collision types that you need to know. The first of the three is called an elastic collision. Now, these three collision types have a connection to kinetic energy, which I'll explain a little later. But for now, elastic collisions are objects that start separate and end separate. Let's take a look at one. So here I have a simulation for two physics carts. The one on the left is 2 kilograms, the one on the right is 1 kilogram. So the red car is moving to the right at 2 meters per second, and the blue car is moving to the left at 7 meters per second. I'm going to let them hit. They bounce off each other. And now the red car is moving to the left at 40 meters a second, and the blue car is moving to the right at 5 meters a second. Let's do an analysis. So here's what I want to do. I want to analyze the momentum in my system, which is both carts, both before and after the collision. And in order to get the total initial momentum, I need the momentum of both carts. That'd be mass A, velocity A initial, the momentum of the first cart, and mass B, velocity B initial, the momentum of the second cart. 2 kilograms times 2 meters a second, plus 1 kilogram times negative 7 meters a second, because the blue cart was going to the left. I get 4 minus 7 kilograms meters per second, which gives me negative 3 kg m over s. So here's the initial momentum. Let's see how it compares with the final. Well, for the final momentum, we have mass A, velocity A final, plus mass B, velocity B final. 2 kilograms times negative 4 meters per second, plus 1 kilogram times 5 meters per second. Negative 8 plus 5 kgm over s, which gives me negative 3 kgm over s. So it is identical, which means the initial equals the final. I'm going to hold on to this equation, and let's see if it's true for all three collision types. So the second collision type is what's called a perfectly inelastic collision. The objects start separate and stick together. Now, in truth, there's a little more detail involved here. Technically, an elastic collision is a collision where kinetic energy is completely conserved. It is neither lost nor gained from before or after the collision. An inelastic collision is technically one where some kinetic energy is transferred to another type. But in a first-year physics course, you are almost solely dealing with what are called perfectly inelastic collisions. These are collisions where two objects start separate and stick together. In other words, it takes energy to stick the two objects together, and that energy comes from the kinetic energy. It turns into another type. So technically, there is a collision type in between these two, simply called an inelastic collision, where the objects do start separate and end separate, but they are extremely rare in a first-year physics course. So I'm going to concentrate on the basic three for now, and maybe come back and make a video on the fourth type later. So, a perfectly inelastic collision. Two objects start separate and stick together. And remember, we're still dealing in one dimension here. So I'm going to keep the same initial settings, although I'm going to set this to an inelastic collision, which means the left side of my equation here is still going to be the same. So these two are going to hit, stick together, and they have the same final velocity because they're stuck together at negative 1 meters per second. So let's take a look at the math real quick. So my entire left side here is the same. However, on the right, I have mass A and mass B. Since they both have the same final velocity, I can actually do this. I just factor it out because I know the final velocity is negative 1. Now, mass A plus mass B is 3 kilograms times the velocity of negative 1 meters per second, which gives me, of course, negative 3 kg m over s. So again, they are equal. Let's take a look at the third collision type. Third collision type is called an explosion or separation. The two objects start together and then separate from each other. This is when I showed you the two carts pushing off each other with the spring plunger. I'm going to start with the one where the two carts are at rest. So the red mass is 2 kilograms and the blue mass is 1 kilogram. Put something in between them so they push off both sides. And I have negative 5 meters a second for the one on the left, which gives me momentum of negative 10 kilograms meters per second. And the one on the right has a velocity of 10 meters a second with a mass of 1 kilogram. So it has the momentum of positive 10 kilograms meters per second, which means the initial momentum was 0 and the total final momentum is 0. All right, so I'd like to show you one more, but this time I'm going to give them a negative velocity this time to start. So they're both moving to the left at negative 3 meters per second. If we take a look at that real quick, it means mass A and mass B are stuck together. They have the same initial velocity. So their combined mass is 3 kilograms times negative 3 meters per second. Total momentum of the system, therefore, is negative 9 kg m over s. They separate, and now I have negative 8 meters per second for the red car and positive 7 meters per second for the blue car. Let's take a look. 2 kilograms, negative 8 meters per second, plus 1 kilogram, positive 7 meters per second. That's negative 16 kilograms meters per second, plus 7 kilograms meters per second, gives me negative 9 kilograms meters per second. So they're equal again. And that brings us to our single biggest rule for momentum, and that is momentum is conserved. The amount you start with is the amount you end up with, and that includes direction. So momentum initial total equals momentum final total. Now, this first equation, it says elastic collision, but this is the momentum collision equation for any 1D collision. This works with any type. The only addition is, if you happen to recognize it as a perfectly inelastic collision, then you can write it like this, where you can factor out VF. This is only really useful if you're looking for a VF or something on the left-hand side. But if you're looking for one of these two masses, then the first equation is better because you need to factor it out anyway. Same thing with an explosion or separation collision. If the two objects are together, you can combine their masses because they have the same initial velocity. However, this top equation is the one you really need to know. So long story short, to the left of the equal sign is before the collision, the equal sign is the collision, to the right of the equal sign is after the collision. And momentum is constant. And that is the actual term the AP exam likes to use. This quantity is constant throughout the entire collision. All right, since I have them, I have a few practice questions if you want. I'm just going to run through the slides. You can pause it and look for an answer, which I will simply put up right after the question. Here's the first problem. 1,200 kilogram car is driving east at 20 meters a second and has a head-on collision with a 2,300 kilogram SUV traveling west at 17 meters a second. The two cars entangle and stick together. What is the velocity of the combined wreckage? A 45-kilogram boy on frictionless skates is at rest. He throws a 12-kilogram medicine ball he was holding to the left at 9 meters a second. What is his velocity after the throw? This is a very common question, by the way. Okay, this is the part I was talking to you about the three collision types. In an elastic collision, kinetic energy is conserved. We're doing energy next, but these are simply what you need to know to identify these three collision types for now. In a perfectly elastic collision, kinetic energy is decreased. Some of it is transferred to what's called internal energy or thermal energy. The AP exam likes to call it internal. You'll be dealing with it as thermal energy in detail in AP Physics 2. In an explosion or separation collision, kinetic energy is increased. The energy is usually stored in something like the spring plunger in the carts. So elastic collision, kinetic energy is conserved. Perfectly inelastic collision, kinetic energy will decrease. And explosion, kinetic energy is increased. All right, I will end this here. Have a good day. This is Mr. M signing off.